Analytical Chemistry 1, Lesson 15. Mistakes happen. We hope that they occur only rarely, but how do we identify them? We know that normally distributed data can have quite a range to it in a series of identical experiments. How do you know if there's a genuine outlier that really should not be part of our data set? We will look at two tests that can help make that decision. The first is called Dixon's Q-test, or more commonly just the Q-test. The Q stands for rejection quotient as developed in the original 1951 paper. It is simple to apply. Arrange your data points in increasing order. The range is the difference between the first and last data points. If there's an outlier, it must be either the first or last one. Choose the one that has the largest gap between it and the next data point. The difference is called the gap. The gap divided by the range is the Q statistic. Dixon's work took the set of data and identified a confidence interval. They would then find the Q statistic, this quotient of gap over range, for the most distant data point in the set. They tabulated critical Q values, which, when exceeded, would suggest that at this level of probability it is likely that this data point is not part of the overall data set. You can consider that point to be an outlier and you can discard it from the data set. Because we are comparing the data point to a confidence interval, it is a two-tailed test. Any data point with this value for Q, whether above or below the average value of the data set, is not likely part of the data set at the given confidence level. Here's an example. This is a data set collected in sequential sampling events. Here's the same set of data organized from largest to smallest. Inspect the first and last data points. Which has the largest gap to its neighbor? Look at the ordered data and look at only the top and bottom entries. They are the only ones relevant to this discussion. You should quickly see that the bottom entry is the possible outlier. Calculating the Q statistic is easily done. It is just the quotient of the gap divided by the total range. The gap to its nearest neighbor and the range is between the top and bottom. For this entry, the Q statistic is 0.491. We want to compare this to the table entry. We have 10 data points and we want 95% confidence in our analysis. And this table is for a two-tailed analysis, so we are asking about the probability of finding a data point with this Q value either above or below the main cluster of data points, and it's still remaining part of the data set. The table value is clearly 0.466. Our calculated Q is greater than the tabulated value. This means that this data point lies outside of our 95% confidence interval, and we can consider discarding it from our work. There are plenty of warnings offered regarding the use of the Q-test. It is best used sparingly. It should never be used twice on the same data set. If you do throw out a data point, it is best if you can explain why it happened. You were distracted, you sneezed, you were watching a reality TV show, the dog drooled in that sample, some explanation. And this is a quote from our textbook. Good common sense and the fortitude to repeat a questionable experiment are usually more valuable than any statistical test. But you can use the Q-test, but do so sparingly. It is interesting to note that Dixon was not a statistician, he was a chemist. This work was first presented at the 1950 American Chemical Society Conference in the Analytical Chemistry Division's sessions. For an alternative tool, here's another method developed instead by a statistician. The approach is similar to that of a Q-test, but we do not need to reorder the data in order to find the gap in the range. Rather, we find the sample mean and standard deviation, and then identify the outlier that we want to test. Here's the data set again. We calculate the average and standard deviation for the data set. Grubbs' test measures the separation between the outlier data point and the sample mean in units of standard deviation. This is the G statistic. The absolute value is useful to account for either a minimum data point or a maximum data point. The Grubbs test is only concerned with how far away the data point is from the mean. The outlier still is the 182.31 data point. Its G value is 2.512, which is to be compared with the critical G value from the table. Here is a one-tailed Grubbs test table. We have 10 data points. We want to test to the 95% confidence level. In the table, we find the value 2.176. The questionable data point's Q statistic is greater than that. We can conclude that with 95% confidence that this data point lies outside the statistically valid range for the data set and can thus be excluded. The similar warnings are offered here again. Use it sparingly, Try to explain your choice to exclude a data point. Both the Q-test and Grubbs' test are standard go-to tests in many disciplines. They can be very useful when trying to clean up your data. It is important that the data follow a normal distribution. When employed in other distribution patterns, they can give very misleading results, but it is a strong test for normally distributed data. The table here is for one-tailed tests. The table entries are calculated from this equation. N is, of course, the number of data points. The t-values come from students' t-table. They are for n minus 2 degrees of freedom, and the probability level, 0.05 for 95%, of course, is divided by n. You can always look up Grubbs' paper and go through the derivation if you would like. If you are in need of a two-tailed test, just change the t-statistic probability from alpha over n to alpha over 2n and use the two-tailed expressions. Always look over your data. Check for outliers. Does it make sense? Use your statistical tools, but never let them do your thinking for you. Make decisions and choices about your data and the conclusions you draw from them. That is your job as a scientist.